In a previous video, we saw how elastic collisions worked. We saw that if object A is going towards object B and object B is going towards object A, then the objects will end up bouncing off of each other. Similarly, if object A is static and object B is heading towards it, then supposing that object A and B both have the same mass, then all of the momentum and hence all of the velocity will end up going to object A while B ends up standing still. Now this is a very particular case, of course. In inelastic collisions, we also saw two cases. We saw that when two objects are heading towards each other as well, then they end up forming this larger mass that is heading in the same direction as the object that had the larger momentum. And in this particular scenario, we assume that A has the larger momentum, so the bigger object will go in that direction. The other simpler scenario was when one object was moving and the other object was static. So this will directly cause the object after the collision to move in the direction of motion of that particular object that was moving. Now, we have seen that the calculations for this are quite straightforward. We saw that they are summarized basically or represented by this formula mv equals mv, and we gave a few examples, or actually just one example. Now, what if we look at this scenario where in an inelastic collision both objects happen to be moving? What will the formula be then? The formula will become a little bit more interesting. So instead of just thinking that object B is static, we're going to think that object B, or we're going to consider that object B is also moving towards object A. And now we ask the question, what are the momenta before and after the collision? So first, we consider the momentum of object A as equal to the mass of object A multiplied by the velocity of object A. This is not surprising. Similarly, the momentum of object B is the mass of object B multiplied by the velocity of object B. Again, not surprising. So the sum of these momenta, the sum would simply be P before equals PA plus PB. Nothing special. So to expand this, we get P before equals MA VA plus MV MB VB. Because we've expanded momentum A into MA VA, and we've expanded momentum B into MB VB. Nothing special, nothing surprising so far. Next, let's look at the momentum after the collision. So the momentum after the collision is going to be M of A plus M of B, all multiplied by the velocity of the object. Now, this might look confusing. Similar to the previous question, we summarized the momentum after the collision as a capital M, capital V. This is exactly what we did. This is exactly what we're doing. So you can write this like that as well. You can say that the momentum after is capital M multiplied by capital V. Or if you want to be more specific, you can say that it's mass A plus mass B, all multiplied by the velocity of this object. So it's up to you really. I will not mind. It can be capital M, capital V as well. Now here's the interesting thing. This is where we draw the comparison between the before and the after image of this collision. We know something extremely important. We know that momentum is conserved. And what does this mean? It means, as we have done before, remember when we said mv equals mv? This is because the collision before is equal to the collision after. Now here, it's the same thing. The momentum before is equal to the momentum after the collision. So we know that the momentum before is this, and we know that the momentum after is this. So we're going to expand each of these. The momentum before is, as we said, this is missing the V over here, so MAVA. The momentum before is MAVA plus MBVB equals the momentum after mv. And this is the formula we're going to be using. This is kind of a proof to you that why is this formula correct? Why is this the formula, the one that we will be using in the case of inelastic collisions? So MAVA plus MBVB, this represents the before the collision, and this is the after.